Okay, welcome to lecture here. Okay, so we're just gonna talk about the rest of this chapter here, kind of finish it up. And obviously we do have exam today, and we'll talk about that in a bit. And stuff. So let us do this. We'll have a short little lecture here, then we will obviously continue on here to our exam. Okay. All right, so we've been talking about coordination compounds, complex ions. We've also been talking about isomers here to finish up on last time. And again, a reminder that basically isomers in general are compounds that have basically the same formula. They're composed of pretty much the same type of elements and so forth. We then have usually some type of different arrangement that occurs when we're doing the sort of arrangement of those guys in three-dimensional space. And there's some different sort of isomers that we've talked about up until this point. Let's see here. You know, we had some coordination isomers in relationship to our coordination compounds. And again, as we saw with this one, essentially they have made up of all the same stuff, but they are basically arranged differently. So again, in the first one here, what we saw was the sulfate, for example, was actually part of a complex ion, while the bromide was more the counter ion in that case. And also in the second one, the bromide then became part of a complex ion, while the sulfate there is a counter ion. Also has some effects, as we talked about as well. As you can see, the overall charge on, say, the bottom complex ion was +2, while the top one was +1. There's also linkage isomers that we talked about, and linkage isomers basically are how the ligands themselves are attached to the metal in the complex ion. So in the case of the NO2- as the ligand, in the top example here, it connected through the nitrogen. In the bottom example, it connected through the oxygen. So that different sort of linkage of how those guys come in will give us some different isomers as well. Again, everything else sort of in there would be kind of the same. So technically it would be composed of all the same molecules, ions, and so forth. But again, somewhere in there, there's a different sort of linkage as to how they come about. We then started talking about sort of stereoisomers, and one type is geometric isomers, which is our cis or trans type of isomer. And again, these are guys that have the same atoms, the same bonds, but again, different bond angles because of sort of how those relatable groups are located. So, for example, here we have our cis isomer here. And cis means, again, as we talked about, sort of the same side, while trans means opposite side. So on the top one there, you can kind of see the NH3s are on the same size, the Cls are on the same size. So that's sort of cis. Again, that's all within the same sort of plane, and that's our square planar sort of geometry. On the bottom one there, we have trans. So you can kind of see that the chlorines, for example, are opposite sides of the plane. And so are obviously the NH3s in that case. So in general, cis means same side, trans means opposite side. And we also see that here in the more octahedral sort of arrangement. And again, sort of above and below the plane there on the first guy, we have the chlorine that's in common, and that would give us our trans isomer. While if we look at those chlorines on the second one on the right, They're more sort of on the same side of the plane, with obviously the square plane kind of in the middle there, being kind of above and below the plane of that molecule here in the middle. So we left off, I think, talking about a little bit about optical isomers. Optical isomers are isomers that have opposite effect on plane polarized light. They typically are non-superimposable mirror images. And these non-superimposable mirror images are usually related to a type of molecule that's basically classified as a chiral molecule. And chiral molecules are those ones with those non-superimposable mirror images. And those type of isomers are sometimes referred to as enantiomers. Enantiomers are mirror images of each other, and so they are these optical isomers, but they are not superimposable as well. So an enantiomer is basically an isomer that is, again, a mirror image. So like we were talking about our hands the other day, if you put one up to the mirror, you get your other hand staring back at you. And although they are mirror images of each other, you can do as much as you like, move it around as much as you like. You'll never get it to correctly superimpose, you know, for example, in the hand example, the hand correctly, again, in terms of thumbs being in sort of the right direction, palms, and so forth. So it's sort of an example here. You could have some light that goes through sort of a filter and comes out in sort of two types of planes, and you can measure sort of the angle at which, you know, these sort of molecules will sort of rotate that light, and that gets us some things like some types of isomers, DL, RS, you know, based on sort of the angle. We don't really get too much into that here, so you don't have to worry too much about that here. Again, here's maybe a better example of the hand sort of idea here. If you take your hand, put it up against a mirror, we get a mirror image. Again, if we pull the mirror image out of the mirror, as you can see in the picture, we can never get it to fit correctly. Although it kind of looks like the thumbs are on the right side here, they are not correct in the sense of one is palm up and one is palm down. So they technically would not be an exact replica of it. Also, if you look at nails, right, nails are down and nails are up on the other one. So again, you could rotate it around as much as you like. You'll never get them to be superimposable. And that's usually a very characteristic of chiral molecules. Something that's known as achiral, which is something you'll learn in organic as well. Achiral means that if you do take the mirror image, it actually is superimposable. So a chiral compound, you could take the mirror image and you cannot get it to fit perfect. If you have something that's more of an achiral compound, you could take the mirror image, and even with some rotation, you could get it to fit perfectly sort of over the original object there. And here's a couple of guys, a couple of isomers here, and they are mirror images of each other. The image of 1 and 2 cannot be superimposed. And again, that's no way that you can kind of get those guys basically to sit perfectly on top of each other. And where the difference is, again, if you sort of zoom in here, is the connectivity that we have in the mirror image versus what we have in the original one. And if you look in the original one, really the main difference is right here. This guy and this guy are connected via here. But when that gets shot to the mirror image, that sort of connection ends up being here and here, which is kind of like around the corner in terms of the connection. So because of that sort of around the corner connection, you'll never get these two guys basically to sit perfectly on top of each other, you know, as you take out that mirror image. Although some parts of it may sit on top of each other because of that sort of difference in sort of how the connectivity occurs in that mirror image, even with sufficient rotation, movement, and stuff like that, is not going to be able to sit perfectly on top of each other. And again, since they're non-superimposable, they then would be sort of chiral and enantiomers of each other. While here, the trans isomer and its mirror image are identical and they're superimposable. And again, that's more of what's sometimes referred to as an achiral sort of compound. But again, here is the mirror image, and here's the original image. And you can see even in the mirror image here, we got these kind of same connections happening on both of them when we look at them. You know, so if we pull out this mirror image, it is going to sit okay on top of it. Again, here, kind of like the one we were just looking at, we have a bond between these two nitrogens up front, but that gets translated to back here. And you sort of get this guy in the way if you want to think about it that way. So every time you rotate it, you now have that little middle guy that's sort of in the way, and it won't be able to sit perfectly on each other. So that cis isomer and its mirror images, again, are non-superimposable, and they are a pair of optical isomers because of that, and what are referred to as enantiomers because of that. Again, some of this is very sort of hard for a lot of people to visually sort of follow along with it. Sometimes it helps to try your best to sketch out something to sort of identify these things. I don't anticipate us going too in detail on a lot of this stuff. I think the activity we'll do tomorrow will have some of this involved in it. But again, without some models, sometimes model kits are very helpful in this. It can be sort of hard to visualize, sort of, it kind of looks the same. I don't understand why it's not, again, because there's very subtle differences in sort of the mirror image. Like if you don't really look at it too closely, you don't realize that, oh, this guy kind of is now in the way of that bond that wasn't in the way over here. And, you know, that's going to not allow it to properly be rotated in any sort of direction to basically fit on top of each other, because that nitrogen-nitrogen bond now is kind of further away in sort of three-dimensional space. So enantiomers basically are two molecules that are mirror images of each other, and they are also non-superimposable. So that's your basic sort of definition of enantiomers. Diastereomers, which are something we're not going to get into, are another sort of form of these type of isomers, and they are not mirror images of each other. So there are two molecules that basically are not mirror images of each other, and you'll probably talk more about that in sort of organic when you get there. All right, any questions on isomers here? So we're going to finish up sort of talking about in this chapter about the idea of the electrons that are involved sort of in these complex ions. And since, as we've been talking about, for the most part, these electrons involved are basically our d electrons, because they do come from transition metals. And we're going to kind of talk about what happens in terms of the distribution of these electrons in sort of the metal by itself when no ligands are attached, and what happens as ligands basically sort of get involved. And some of this, you know, is based on sort of a localized electron models, sort of ideas of bonding, and some geometries that we think about in terms of bonding, and similar types of geometries that we see here in these complex ions. So some things in terms of bonding and things that you should be familiar with, right? It's formation of things like hybrid orbitals. Hybrid orbitals, as you may be familiar with, right, are like sp, sp2, sp3, sp3d, sp3d2. Those are what we take atomic orbitals, right, which are s's or p's or d's, and we basically hybrid them together, or kind of mix them together, and we get these sort of hybrid orbitals. And again, sort of the benefit of hybrid orbitals in terms of bonding is it allows us to see some of the bond angles that we see in certain molecules. And because it now creates these hybrid orbitals, which technically are sort of the same shape, they're on the same energy sort of level. So it allows for better bonding between those hybrid orbitals, again, as opposed to trying to take like an s orbital that's like a circle, a p orbital that's a figure 8, and trying to squish them together and stuff like that. So that's one sort of model of bonding you're probably familiar with. The Vesper sort of model in terms of geometry doesn't work perfectly for complex ions. There is a little bit of some overlay in terms of names and geometries that we sort of associate with certain complex ions. So not perfect, but we do use a little bit of it in sort of conversation in terms of these geometries associated with the complex ions. And when we sort of think about sort of what's happening with these guys, we sort of think about it more as an acid-base concept, and again, more of that Lewis acid, Lewis-base concept, whereas we talked about, again, a Lewis acid is a electron acceptor, while a Lewis base is an electron donor. And and obviously, in terms of complex ions, the hybrid orbitals that may be used will depend on the number of ligands that are attached. So for example, here we have a set of 6 sp3d2 hybrid orbitals in the cobalt complex, kind of coordination number 6. And again, if you just kind of think about Vesper, 6 is that expanded octet, which is that octahedral arrangement, right? So when you have 6 electron pairs, right, that is your octahedral arrangement that's happening. And again, we could kind of envision these guys, as we said, more of a Lewis acid base. We could see the electrons sort of coming into our d orbitals, right, and sharing and giving those electrons over. Other sort of geometries very common with complex ions is tetrahedral. And you could kind of think about tetrahedral like Vesper. Here we got 1, 2, 3, and 4. So kind of like 4 electron pairs, right? In normal geometry is tetrahedral. So sort of the similar idea. This guy, which is square planar, again, is that expanded octet. But if you think about just what's happening with our square planar, we still also have really that 1, 2, 3, and 4 sort of bonding aspect to it. But it is an expanded octet, so it does get into that sp3d2 sort of arrangement, and also sort of has 4 bonds. So these are very common that we see with coordination numbers of 4, as you could kind of imagine. And here, similar again to sort of bonding as well, we got 2 sort of guys going on there, and 2 right sort of electrons is a linear sort of geometry. So again, although Vesper doesn't work perfectly sort of for complex ions, these are very common sort of complex ions that we see in terms of the geometry, and obviously related to our coordination number of this guy would be something like a coordination number of 2. So so with our coordination number 4, you do sometimes have some choices in terms of the geometry that you'll see. You'll sometimes see it as tetrahedral. Again, more of that normal tetrahedral geometry and bond angle 109.5-ish. And again, some will have more of that sort of expanded octet like you're familiar with in terms of the geometry of square planar. And like I said, in terms of relationship to coordination number, you can sort of think about it that way in terms of, you know, it's very similar to when you count up electron pairs for your geometry. Again, you can kind of think of the coordination number very similar to that. So again, giving us more of a linear shape, a coordination number 4, you're either going to get that tetrahedral shape or really that more square shape there, that square planar shape, more of that 90-degree sort of bond angle. And then in 6, in terms of coordination number, is going to basically relate to our octahedral. So let's talk about what happens with those electrons in those metals when we are have no ligand present. So again, because the metals in our complex ions are typically transition metals, we're basically dealing with our D subshells, right, and our D electrons. And again, a reminder, these are our 5D orbitals. And obviously each orbital, as like normal, can only hold 2 electrons. So in the absence of any ligands, so when you have just sort of the metal by itself, no ligands attached, all 5 of those guys, you know, kind of like what you did maybe in orbital diagrams when you drew electron configuration, you know, all 5 of those d orbitals are essentially equal in terms of energy. So they're all sitting sort of perfectly equal in terms of their energy at where they're at. But what actually happens as we start adding ligands to it is there's actually a shift that occurs. There's a shift that occurs in terms of these 5 d orbitals, in terms of their energy. And when we look at that, these 5 d orbitals, which is what these boxes represent, will actually go through sort of a splitting that occurs. And in this case, what we're looking at, by the way, is like a coordination number of 6 and some octahedral sort of geometry is sort of what we're looking at in this sort of example specifically. And what happens in this sort of arrangement is we get 3 of these d orbitals. So your XY, your YZ, and your XZ orbitals heading down on the bottom. And up on top, you had your X squared, Y squared, and your Z squared heading up on top. And the consequences of this is that now we have a set of d orbitals which are lower in energy, and we have a set of d orbitals which are higher in energy. And the difference in terms of energy between the lower set of d orbitals and the higher set of d orbitals, that is what is known as crystal field splitting, sometimes just abbreviated with the delta. Sometimes that energy difference is delta E, so you'll sometimes see both of them sort of used. So that crystal field splitting is basically the energy distance that basically occurs between one set of d orbitals and another in the presence of a ligand. So as those ligands like NH3 or something like that comes in, these d orbitals, which started out equal in energy, now gets sort of a switch. And that's really important in terms of how electrons basically will be put into that d orbitals for bonding. So in general, as you hopefully know, when you have a set of d orbitals such as this, the maximum number of electrons, right, you can put into an orbital looks something like this, which is 2. And the way that they go in, hopefully you remember as well, they go basically one at a time, right? So they fill it up one at a time. And then what they do is they come back and then start pairing off, right? So that is the normal way, right? Electrons basically would fill the d orbitals if you're doing something like electron configuration and writing those electron configurations. And because we get this sort of splitting that occurs in our atom here of those d orbitals when those ligands are coming in, it affects what happens in terms of these electrons. So for example, what's going to happen is obviously electrons, as you know, go in the lowest energy first and then go off to the next lowest, and so forth. So when these electrons would come in here, the first one would go here, second one would go here, right? And third one would go here, as they are all pretty much even. And now what happens if we have, say, 4 electrons, it has to make a decision. It has to decide, is this distance between these lower d orbitals and the higher d orbitals, is it really big or is it not so big? If it decides, well, the distance between the lower guy and the higher guy, it's not that much, then what you will have is the electrons would continue to fill like normal, right? And come back and go back through and basically fill it. Now, if you get to a point where you start putting those electrons in, and it's very small, and we get to those electrons and it decides, well, I'm going to fill my electron here, going to fill my electron here, a little sideways, going to fill my electron here. And then it looks and goes, whoa, that's like way up there. That's kind of very far. I don't really feel like that. That's a big spread in terms of the energy. What's going to happen is instead of that fourth electron going to the higher orbitals, it's going to decide, I think I'd rather just go this way first. And it will fill up these bottom ones first until it has no choice, and then go to the top one. So depending on how big this sort of crystal field splitting is, will have a big effect on sort of how those d electrons are basically distributed in a particular complex ion. And that's going to be really important because, and depending on the situation here, you could get a lot of unpaired electrons, which is sometimes referred to as being paramagnetic, unpaired electrons, having unpaired electrons. Or you could get a lot of paired up electrons like we do in this particular case. And that could have some effect on sort of the type of complex ion that you will have. Now, there is a way to sort of measure that crystal field splitting, that energy difference that occurs between those different d orbitals. And to do that, you do use an equation that you probably have seen before. This is essentially that energy equation, right? E is equal to h times the frequency, right? H is Planck's constant. Nu here is our frequency, right? Typically is reciprocal seconds. You may also remember that C is equal to the wavelength times the frequency, which means that the frequency is equal to C divided by the wavelength, which means if you put this in here, you get HC over the wavelength as another sort of version of that. And again, this is sort of how you could actually calculate that crystal field splitting. Obviously, if you're going to do this, on the left there is a absorbance curve. And as we saw in some of the labs we did earlier, and we've talked about, I think at this point as well, that obviously when we set up the spectrophotometer, we do want to make sure that we choose the maximum wavelength of absorbance. So in this particular case, you would probably choose a wavelength somewhere in this area, as again, that would allow all of your samples to basically come within the range. So let's take a look at sort of an example of doing this, and I think it might even be filled in on your paper, so we'll just kind of go through the calculation just to make sure. There we go. So first off, we have this complex ion here, which obviously now you should be able to name that hexamine cobalt 3 ion, right? Occurs at 470 nanometers. What is the color of the complex ion, and what is the crystal field splitting? So a couple of things that we also touched upon earlier on in some experiments, but just to sort of reinforce, remember that when we do see a color, so for example, let's say our color looked red, what that means is what we actually see is the complementary color to what we see. I'm sorry, I'm going to say it again. So what we see is actually the complementary color to the wavelength of light that's being absorbed. So if our color of our solution looked red, the wavelength of light that's being absorbed and where we would want to set something like our machine to would be in this green, the complementary color to red. In this green area in terms of wavelength will allow us to see a red color. And again, the light that would be absorbed would be in this green area. So at 470, if the absorption happens at 470, which is in this area, again, this is the color that is being absorbed. So to us, it will look like the complementary color, and the complementary color to blue there is orange. So if we were setting our machine and we had the solution in front of us to test the absorbance values, it should appear orange to us. And again, we would set our wavelength at 470. And again, that sometimes confuses people, like my solution looks orange. Why am I setting the wavelength to an area in the blue part of the spectrum. And again, it's that reason. What's being absorbed, we see the complementary color basically to that. And since we do have the wavelength, we can basically use that energy equation, which again, as I said, sometimes for crystal field splitting, people will just use the kind of delta sign for that, and our hc over the wavelength. Again, both of these are constants. C is the speed of light, right, which is our 3 times 10 to the 8 meters per second. That's our Planck's constant. As you hopefully remember, when you use this equation, you do need to convert this to meters, right? So it's in nanometers, and that's why the conversion was done right here. So again, this is our Planck's constant. That is our speed of light, and that is our wavelength that has been converted into meters. And we do that so that the meters will cancel, the seconds will cancel, and we will be left with joules when we calculate that, which is a unit of energy, which is good. Again, that's that crystal field splitting energy, the energy difference between the lower d orbitals and the higher d orbitals. And since we're looking for it per mole, that is basically the joules per atom. So that is why we're using Avogadro's number to go from atoms to moles. So we do need to incorporate Avogadro's number here to do that, to take us basically from joules to joules per mole, and divide by 1,000 gets us to kilojoules per mole, which is here at 255 kilojoules per mole. So that again, energy represents in this complex, which again, if we look at this complex ion, has a coordination number of 6, should probably have that octahedral geometry, and should have the splitting that we just saw on the previous page, where it has the 3 d orbitals on the bottom, the xy, the yz, and the xz, and the 2 d orbitals up on top, your x squared, y squared, and your z squared in terms of our d orbitals. So this is the splitting pattern, and what we just calculated is the difference here in energy between those lower set of d orbitals and those higher set of d orbitals that are present. Any questions on that there? Okay. Now, how do we know if the splitting is going to be sort of small? Is it going to be large? You know, how can we sort of determine that? And the way we could sort of determine that is by looking at this. This is what is known as a spectrochemical series. And it basically breaks up very common ligands into basically 2 types. There's what is referred to as a weak field ligand, and there's one which are referred to basically as a strong field ligand. And kind of like what the names imply, if it is a weak field ligand, that means that when we get that separation of those d orbitals, I'll just dramatically draw it like this, that separation, that crystal field splitting is going to be relatively small. And what that means is when electrons fill these d orbitals, they will decide to fill it just like normal, you know, one at a time, go to all of them. Now, if we get somebody that is a strong field, what that means is when those d orbitals split, I'll dramatically draw it. I'm not sure it will really be that big, but we'll dramatically draw it there. And what that means is we're going to have a very large change in energy, or crystal field splitting energy. And what that's going to do in terms of when those electrons come in is they're going to decide that's way too high up there. I'm just going to kind of fill in down here first. And then if they're forced at that point, they will find their way up there basically to do that. So again, depending on whether it's a strong field or weak field, as to sort of what you will see occur in terms of the electrons being distributed. Now you may ask, like, what's the deal in the middle? And it's a good question. What is the deal in the middle? Who knows? But they will oftentimes, for those guys in the middle, are if it could be sort of, you know, in certain cases strong or weak, they oftentimes will give you some type of information in the problem. So they'll say, hey, do it for strong field, or do it for weak field. So they'll give you that sort of information. They will also perhaps give you some information like do it for high spin or low spin. And high spin complexes means that you have a lot of unpaired electrons, kind of like over here. If we look over here, we got 1, 2, 3, 4 unpaired electrons. And low spin complexes are ones where you have more paired electrons. Like here, we pretty much have all paired. We only have one unpaired electron. This would be considered low spin. And that is pretty much how that usually will occur. In a weak field, you'll get a more high spin complex because they could kind of go in one at a time like normal, really spread out to all 5 of the d orbitals. In a strong field, you will sometimes get a lot more pairing off that occurs with those electrons, thus not leaving you as many unpaired electrons happening. So let's take a look at an example here. So for example, let's take a look at, what do I want to look at there? Let's do FeF6 3 minus. So let's do FeF6 3 minus. Yeah. And when we look at this sort of complex ion, we want to figure out some things like normal. So we want to figure out what is the oxidation state on the iron. So the F is -1, that's -6, which means the iron here is +3. Now, if we look at the electron configuration for iron, with no charge, right? The electron configuration for iron with no charge is 26. And when we look at it, it is like argon 4s2, 3d, 1, 2, 3, 4, 5, 6, 6. So when it becomes iron with a +3 charge, as we talked about, the s electrons are going to be lost first. We then need to lose 1 from there. So we're going to end up with argon 3d5 in this particular case. So iron with a +3, and we'll come here. This is our iron with a +3. It's going to have 5d electrons. So when it comes, it's going to split off into this arrangement. It's going to split off into this octahedral arrangement because the coordination number here is 6. So it will do this splitting here with these d orbitals on the bottom, the other ones up on top. So the important part is when we look at F here, you know, F is sort of to the weak side. So we will do this as a weak field. And if this is a weak field, what that means is the separation between these orbitals are not going to be extremely high. So what's going to happen is, in that case, we will have something that looks like this. Let's draw it here. And the 5 electrons for iron would be distributed like you would expect, 1, 2, 3, 4, and 5. You can see here we have 5 unpaired electrons in this complex ion. They are all unpaired, which means that it is definitely going to be a high spin complex. That is a lot of unpaired electrons. Any questions on that? Now, if we switch it up and we change the ligand and we go with CN instead, so if we look at this exact same metal and we go with, we'll go here, FeCN6, also with a -3 charge. If you do sort of the charge on the iron, again, going to be -1, going to be -6, going to give us +3. So again, in the second situation, our iron is +3, going to be starting with those same 5 electrons. Now, though, the ligand is CN, which is over here, and that is a strong field splitting. So we'll use these boxes here to represent this bigger split that's happening. Now, when we go to distribute these 5 electrons in the iron 3, we will have 1, 2, 3, and at that point, it's going to decide that is like way too up there. I ain't going up there. I didn't sign up for that. I'm going to come back this way and start to pair off here first. And what we see is in this particular case, we are actually left with only 1 unpaired electron. And that would be representative of what is referred to as a low spin complex. So these are very common questions that are asked in sort of complex ions and stuff like this is, is it high spin? Is it low spin? How many unpaired electrons would you imagine? And to be able to sort of draw these pictures. Any questions on that? So again, the important part is the electrons that we're sort of distributing does come from the metal that's in the complex ion, and how many you distribute come from basically how many d electrons are left over after it gains a charge, obviously, or whatever the charge may be. And that's why it ties together, importantly, what we talked about in terms of transition metals, that transition metals typically will lose the s electrons first, like we did up here. And again, that is how we lose those 2 electrons and be able to dip into the D's there after that. So here's that, what I just drew there. And again, many unpaired electrons resulting in a high spin complex. So again, if they tell you to do more of a high spin, it probably means that you could think of it as a small crystal field splitting. While if they tell you it's more of a low spin, this splitting here is going to be strong field or larger splitting. Here's an example of all those sort of different splittings that can occur with depending on how many electrons that you have going on. And again, you can see for the most part on the left-hand side, all of our high spin, which has the most unpaired electrons, does occur, as you can see there, from d orbitals, which are closer together, a weaker field and a smaller splitting that's occurring, as opposed to, again, when we have a larger splitting that's occurring on the right, we get a lot more paired up electrons and what is referred to as being more low spin. So what we were talking about here, just to reiterate, is specifically, and when I'm talking about specifically, I'm talking about how these orbitals are split, is again for complex ions with a coordination number of 6, and that octahedral arrangement is how these d orbitals basically will split. Now, when we are dealing with something that is not a coordination number of 6 and not octahedral, there is also splitting that occurs. So we talked about a couple other geometries. We talked about tetrahedral geometry and then also square planar. And those are guys with coordination numbers of 4 typically. And let's look at what happens when we are talking about the splitting that occurs with our tetrahedral arrangement or a coordination number of 4. So that is what we're looking at here. Again, tetrahedral, and probably going to result from that coordination number of 4 in the complex ion. We see a very similar splitting pattern that has occurred. The only difference is it's opposite of our octahedral arrangement, right? Coordination number 6. So in the previous one, these 3 guys were on the bottom and these 2 guys were on top. So here in tetrahedral, there's actually sort of a reverse splitting that occurs. But it works the same way in terms of distribution of those electrons. Again, if we were going to distribute it, we would start in our lowest energy like normal. And if this splitting is too big, it would, again, start to pair up here first before it moves up here. And obviously, if it wasn't very big, it would go one at a time and then come back and pair off, just like we talked about in the previous one. So if the field was weak field splitting on this guy, again, it would just go in like normal. kind of filling everybody up and then coming back and pairing off and so forth. So tetrahedral, again, works the same way, but again, this is the splitting that we see in our coordination number 4 with that particular geometry. Now with coordination number 4, we also talked about the idea of square planar. And its splitting also occurs, but it gets a little crazy that's going on there. So you get this weird sort of splitting that's occurring where, we got some guys in the way of each other like it normally would be. So same sort of idea as to the other ones. Again, it would feel lowest energy and then kind of work its way upwards in terms of the splitting. We're not going to worry too much about square planar in terms of the splitting. So for us, I'm going to say we're going to stick to just octahedral and tetrahedral. So for us, we'll just stick with those two, which are a little bit more straightforward than this guy here with the square planar. But again, here's what the square planar looks like. So for us, that's what you need to know is, again, in terms of the splitting, our octahedral splitting, like we've been seeing here, and then our tetrahedral splitting, in case you get a Jeopardy question, right? The square planar splitting, but we won't have any square planars. We'll stick to just those two just to kind of make it a little bit more easy, I guess. And that question on sort of how to do that. So why don't we take a look at a couple of examples here and see if you can sort of figure out what's going on here. Let's go with, for each of these, let's see this. Let's do this one. And let's do this one here. All right, so for each of these, why don't you figure out, why don't you draw the energy diagram there with the arrows. Why don't you figure out how many unpaired electrons you got and see what you come up with. In case you don't have a periodic table, that's number 22 on the periodic table. Nickel is 28 and cobalt is 27. All right, so take a few minutes there and try to figure out what you got going on, and then we'll talk about it. Okay, so let's take a look and see how we're doing. Since I remember where I put my writing utensil there. There we go. All right, let's take a look first off at the first one here. And the first one is our TiH2O. And again, you may ask, well, H2O is dead center. I don't really know, which way it is, or, is it strong or is it weak? It really didn't tell us. And let's see if it does sort of matter or not in this particular case. And I'll explain that in just a second. So when we look at water, it's 0. And obviously the overall guy here is +2, which means the Ti is going to have a +2 charge. Now, since Ti with no charge is 22, that's going to give you argon 4s2 and 3d2. Okay. Which means when it becomes Ti with a +2 charge, it only has 20, which means, as we've talked about, it is going to lose those right there, which means that we will be left with 3d2. Now, the coordination number here is 6, which means we're going to get our typical octahedral splitting that's occurring. And again, if you want to be super specific here, you can write in your actual labels. Probably better than I just did there, maybe. Net, what we really have, though, to distribute, say that right, distribute, is 2d electrons, which means the electron is going to go here and here. And in this particular case, as you can see, it doesn't really matter if I know it's strong field or weak field, because I'm not getting anywhere near there in terms of needing to decide that. So this is sometimes what will happen with these is they may not specify anything, might not tell you do it for strong field, do it for weak field, or anything like that. So what that usually will mean is if they don't sort of give you direction, much like this one, it really doesn't matter sort of the ligand that's attached in this particular case, because we are basically only distributing 2 electrons, which are always going to end up down here unpaired. Obviously, it has 1 and 2 unpaired electrons and would obviously probably be classified as a high spin complex because of that. Any questions on that first one there? Okay, let's take a look at the second one and kind of try to do our number 2 here, which is nickel and Cl. And nickel and Cl in this case, let's figure it out. So we got -1 for the Cl, that's -4. That means in this case, the nickel is going to be +2. So nickel, which is 28, again, nickel with no charge, going to be argon 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8. Nickel with a +2 means that it is actually going to have 8 electrons to distribute, and it's going to lose those 2 right there, and nickel will end up with argon 3d8. It also, in this particular case, has a coordination number of 4, and we'll assume tetrahedral since we talked about we're not doing the other one. So we'll go with the tetrahedral arrangement. And that tetrahedral arrangement, right, is the opposite of what we've been seeing. So it is the opposite of this guy, where the 3 actually are higher in energy than the 2 lower guys. And it's all these 3 guys up on top. So we need to decide about our Cl. And if you look at that list, Cl is on the left there, which means it's weak field, which means that this is a small separation. So when we put our electrons 1, 2, 3, 4, 5, 6, 7, and 8, in terms of our electrons that get distributed, we see that we have 2 unpaired electrons in this case. We have a lot more paired electrons, and this most likely would be considered a low spin because of all the paired off electrons sort of complex. Any questions on that one there? And that brings us to our last one that we're looking at. And our last one that we're looking at is the CONH36. Same idea here. This is going to be 0, which means the cobalt here is going to be +3. Get a fresh page. Cobalt, no charge. Argon, 4s2. And what we got there? Cobalt, right? 1, 2, 3, 4. 3d7. Cobalt, we had a +3 on that one, right? Yep, +3. That means that it's going to lose 2 of these guys and 1 of those guys. And that's going to leave us argon 3d6. Those 6 electrons are what's going to need to be distributed. Coordination number here is going to be 6. So we will have our octahedral splitting, which will look like this. And in this particular case here, we will have 1, 2, 3. And at this point, with NH3, we could technically do it both ways, depending on what was told to us. If we did it as strong field, which it did not tell us one way or the other, so we'll do it both ways real quick. So if we do strong field, what that means is we're going to pair off. And if we did weak field, would look something like this, where it's a much more high spin, right? In this particular case. And what would the choice be here? To be honest with you, for us, we're probably not going to get too much into that. It would probably tell you either do strong field or weak field. But, you know, it probably would go more with everybody being paired off over here. All paired off, lower energy, all the electrons is probably the better choice in terms of stability, right? Everybody lower in terms of energy. But again, for us, you don't have to make sort of those decisions. So in a normal problem, it would ask you to do it either as weak field, strong field, high spin, or low spin. If it told you high spin or weak field, you do the guy on the left. Strong field or low spin, you would do the guy on the right. Any questions on how to do those things there? Okay, that should wrap this chapter, I think. So again, just a reminder on that last stuff there, you're responsible for octahedral splitting, tetrahedral splitting, and those are the similar type of questions that you're asked to do. Write the electron configuration, draw the orbital energy diagram with the arrows, decide if it's high spin, low spin, and obviously how many unpaired electrons. Any questions like that? Okay, we're going to stop there today. We are going to take our exam at around 3. We'll start, so you get like 20 minutes there to kind of stretch and all that good stuff. A couple reminders as well here before we go over to the exam. Again, I should not mute myself while I'm giving you these important things. Let's try that without the muting part. You should obviously have your camera enabled. You do need to log into the Zoom. You need to stay in the Zoom the whole time, right? While you're taking the exam, you should not leave the camera view for any reason. So make sure you use the restroom or any of those type of things. You should not have out anything that you should not have out other than a calculator and something to write with. And like normal, you need to obviously send me a private chat when you are done to tell me you're about to upload it, which should be done obviously at an appropriate time. So before we end here though, in terms of the camera angle, let us, for this one here, make sure that obviously, like I said, I do need to see your work area, but I do need to kind of see you as well. So I don't want to just see like fingers coming in from the screen and writing. So try to do sort of a wider shot, if you will, where I could still see your paper work area and what's out and what shouldn't be out, you know, and all those things. And I could kind of see you as well. So, you know, I know it's you that's taking it and all that good thing. And it's not weird, like just hands coming into the screen and writing things like that. So You don't have to be super zoomed on your paper or anything like that. Please zoom it back a little bit that I can still see the work area where you're working with your paper, and I can still see you as well, right? I can kind of recognize that there's somebody sitting there throughout the whole exam and all that good stuff. So in this 20 minutes, 25 minutes, whenever we start, try to get that sort of camera angle a little bit in that range where, again, not so super zoomed that it's just like fingers coming into the screen and I'm seeing things writing. Okay. Any questions on that? All right. So we'll start about 3-ish. And again, make sure you take care of everything you need to take care of. You know, if you need to print it, get that all done and everything like that as well. All right. I'll see everybody in a bit.